there is a wall at the edge of the solar system. Not a wall made of rock or metal or anything you could touch. A wall made of pressure. A wall made of magnetic force and streaming particles, and the ancient collision between everything our star has ever exhaled and everything the galaxy has been quietly pushing back. It is real. It has a location. 2 human-made machines have crossed it, and what they found on the other side did not match a single major prediction that 50 years of careful physics had produced. The magnetic field was wrong. The temperature was wrong. The energy budget did not balance. The shape of the boundary itself was wrong. The wall was thinner, sharper, and more magnetically alive than any model had described. Tonight, on the Science Pillow, we are drifting outward, past the planets, past the last light of the familiar solar system, toward a boundary that separates everything we have ever known from the true interstellar dark. There are no advertisements in this video. The journey is gentle. The pace is slow. And the story we are following is one of the most remarkable in the history of human exploration. Let us begin. To understand the wall, we first need to understand what builds it. And to understand what builds it, we need to begin not at the edge of the solar system, but at its center, at the star. Every second, without pause, without interruption, for roughly 4.5 billion years, the star at the center of our solar system has been exhaling, not breathing in the way you breathe, with lungs and rhythm and the quiet motion of a chest rising and falling beneath a blanket. The star breathes outward in only one direction. It exhales continuously, a stream of charged particles, electrons and protons and heavier ions, flung from the outermost layers of its atmosphere at speeds that would carry them from the Earth to the Moon in roughly 5 minutes. This outward breath is called the solar wind. It is not a gentle breeze. Near the star, it moves at roughly 1 million miles per hour. It carries with it the star's magnetic field, stretched and pulled outward like threads of silk drawn from a spindle, winding into an enormous spiral that fills the space between the planets and extends far, far beyond them. The solar wind does not stop at the last planet. It does not know where the planets are. It simply flows outward, thinning as it goes, losing pressure as it spreads across an ever larger volume of space, but never stopping, never turning back until something stops it. Something does stop it. Far beyond the orbit of Neptune, far beyond the cold, drifting ice of the Kuiper Belt, far beyond every object large enough to have a name, the solar wind runs into resistance. The galaxy itself pushes back. The space between the stars is not empty. It is filled with its own thin gas, its own magnetic fields, its own pressure, generated by ancient supernova explosions and the accumulated stellar winds of billions of other stars across billions of years. This interstellar medium, as it is called, presses inward against the solar wind from every direction simultaneously. And somewhere out there, at a distance that depends on the balance between the outward pressure of the solar wind and the inward pressure of the interstellar medium, the two forces reach equilibrium. The solar wind can push no further. The galaxy will yield no more. At that distance, there is a boundary, a surface, a wall. On one side of it, you are inside the heliosphere, the vast magnetic bubble that the solar wind inflates around the star and everything that orbits it. On the other side, you are in interstellar space, a different physical environment, governed by different forces, filled with different particles, threaded by different magnetic fields. The boundary between these two environments is called the heliopause, and it is the wall at the edge of the solar system. The wall is not at a fixed distance. It breathes, in a sense, expanding outward when the solar wind blows harder during periods of high solar activity, and contracting inward when the solar wind weakens. But its average position lies somewhere around 120 astronomical units from the star. 1 astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. 120 astronomical units is more than 11 billion miles. At that distance, light itself, the fastest thing in the universe, takes nearly 17 hours to make the journey from the wall back to the Earth. If you stood at the wall and looked back toward home, the star would be a bright point of light, brighter than any other star in the sky, but no longer a disk, no longer recognizably a sun. Just a star among stars, distinguishable only because you knew which one it was. The planets would be invisible. Earth would be invisible. Everything you have ever known, every city and every ocean and every mountain and every person, would be contained within a region of space too small to see from the wall. And yet the wall would be real beneath you. Not solid, not something you could stand on, but a transition as definite as the surface of a lake. On one side, one kind of medium. On the other side, another. The crossing takes only a few months of travel at the speeds the Voyager spacecraft achieved. A few months to pass through a boundary that separates the domain of our star from the domain of the galaxy. That is thin. Remarkably thin. Disturbingly thin in the view of the physicists who had expected something much thicker. But we are getting ahead of ourselves. Before the wall could be measured, something had to reach it. And reaching it required a journey that began with an alignment of planets that occurs once every 176 years. Part 1. The Machines That Would Not Die. In the summer of 1977, 2 spacecraft were prepared for launch at Cape Canaveral in Florida. They were not the largest machines ever built for space. They were not the most expensive. They were not even the most technologically advanced by the standards of their time. But they were designed with a care and a redundancy and a conservatism that would prove, over the following 5 decades, to be among the wisest engineering decisions in the history of the space program. Each spacecraft weighed roughly 1,800 pounds. Each measured about 10 feet across its main body, with a large parabolic dish antenna nearly 12 feet in diameter mounted on top for communicating with Earth. The dish was the spacecraft's lifeline. Without it, no data could be sent home, no commands could be received, and the machine would become a silent, drifting artifact, still moving but no longer connected to the civilization that had built it. Extending from the body on booms and platforms were 11 scientific instruments, each chosen to measure a different aspect of the environments the spacecraft would pass through. Cameras for imaging, spectrometers for reading the chemical fingerprints of atmospheres and surfaces, a magnetometer mounted on a long boom to keep it far from the spacecraft's own electrical systems, which would otherwise contaminate its readings with their own faint magnetic signatures. Charged particle detectors designed to count and characterize the protons and electrons and heavier ions streaming outward from the star. A plasma science instrument, present on one of the 2 spacecraft, built to directly measure the solar wind's velocity, density, and temperature. A plasma wave system on both spacecraft, tuned to detect the oscillations that ripple through ionized gas when it is disturbed, providing a different window into the properties of the medium surrounding the machine. Power came from three radioisotope thermoelectric generators. These were metal cylinders containing pellets of plutonium-238, a radioactive isotope whose steady decay produced heat. Thermoelectric junctions converted that heat directly into electricity, with no moving parts, no turbines, no generators. Nothing that could wear out or seize or break. At launch, the three generators on each spacecraft collectively produced about 470 watts of electrical power. Barely enough to run a few household light bulbs, but the instruments had been designed to operate on fractions of that total, each one sipping power carefully. And the mission planners had built in the ability to turn instruments off one by one over the years as the plutonium decayed and the available power slowly declined. The power would drop by roughly 4 watts per year. The mission planners knew this. They planned for it. They wrote detailed schedules specifying which instruments would be sacrificed first and which would be kept running the longest. Those schedules, drafted in the early 1970s by engineers who expected the mission to last 5 years, perhaps 10, would eventually govern decisions made 50 years later about which measurements to keep and which to abandon as the spacecraft drifted through interstellar space on a power budget that could barely illuminate a single dim bulb. The two spacecraft were called Voyager. Voyager 2 launched first, on August 20th, 1977. Voyager 1 followed 16 days later, on September 5th. Despite launching second, Voyager 1 was placed on a faster, steeper trajectory that would carry it past Jupiter and Saturn more quickly than its twin. This was deliberate. The mission planners wanted Voyager 1 to reach Jupiter first, to serve as a scout, to identify any hazards or surprises that might require adjustments to Voyager 2's path. The faster trajectory meant that Voyager 1 would quickly overtake Voyager 2 and would remain farther from the star for the rest of the mission, which is how the spacecraft that launched second came to be the one that traveled farther and faster than any human-made object in history. The reason these two machines were launched in 1977 and not in any other year was an alignment, a rare geometric arrangement of the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, that occurs only once every 176 years. In this alignment, the planets are positioned along a path that allows a spacecraft launched at precisely the right moment to visit all 4 of them in sequence, using the gravity of each planet to accelerate and redirect toward the next. This technique, called gravity assist, had been understood theoretically for years. A spacecraft flying past a planet on the correct trajectory borrows a tiny fraction of the planet's orbital momentum, gaining speed without burning any fuel. The planet, in exchange, loses an infinitesimally small fraction of its own momentum, slowing by an amount so small that it would take more decimal places to express than any instrument could measure. A scientist at NASA's Jet Propulsion Laboratory had identified the upcoming alignment in 1965. He calculated that a spacecraft launched in the late 1970s could use Jupiter's gravity to reach Saturn, Saturn's gravity to reach Uranus, and Uranus's gravity to reach Neptune, completing a grand tour of the outer solar system in roughly 12 years. Without gravity assists, reaching Neptune under the propulsion technology available at the time would require decades, long past the operational lifetime of any spacecraft then conceivable. The gravity assist trajectory compressed the journey into a time span that the instruments and power systems could survive. The mathematics required to execute this trajectory were extraordinarily precise. Each planetary encounter had to be threaded with accuracy measured in fractions of a degree. A small error at Jupiter would cascade through the subsequent encounters, arriving at Saturn as a larger error, growing further at Uranus, and potentially missing Neptune entirely. The navigators who planned these trajectories worked with slide rules and early computers, refining their calculations over years, checking and rechecking every parameter, because they understood that there would be no second chance. The alignment would not come again until the 22nd century. NASA approved the mission formally in 1972, giving the engineering teams 5 years to design, build, test, and deliver 2 spacecraft capable of surviving a journey longer and more demanding than any previously attempted. The engineers approached the task with a philosophy that would prove prescient. They built redundancy into every critical system: duplicate computers, backup thrusters, multiple ways to orient the spacecraft, alternative communication modes. They assumed that systems would fail because systems always fail, and they designed the spacecraft to continue functioning after those failures. They could not have known that the redundancy they built in the early 1970s would be invoked 50 years later to repair a computer chip corrupted by a cosmic ray strike while the spacecraft drifted through interstellar space more than 15 billion miles from the nearest repair facility. But the philosophy that led them to build those backups is the reason the machines are still alive. Both spacecraft carried something beyond their scientific instruments. Bolted to the body of each machine was a golden record. A 12-inch disc of gold-plated copper, encoded with 115 images of Earth and its life. Greetings spoken in 55 human languages. Natural sounds ranging from ocean waves to birdsong to a humpback whale, and music from 27 cultural traditions spanning every inhabited continent. The selections included Bach and Beethoven, a Navajo night chant, a Peruvian wedding song, a piece of traditional Bulgarian choral music, Indonesian gamelan, Japanese shakuhachi, and Chuck Berry. The cover of each record was engraved with diagrams showing how to decode the contents using a rotating needle, along with a pulsar map that identified the location of the star that had sent the spacecraft, expressed in terms of the precise rotational frequencies of 14 pulsars, whose positions in the galaxy would serve as a kind of cosmic address. The people who designed the golden record understood what the spacecraft would become after their instruments fell silent. They would become artifacts. Drifting objects in the interstellar dark, moving at tens of thousands of miles per hour relative to the stars, following trajectories that would carry them through the galaxy for billions of years. Gold does not corrode. At the temperatures of interstellar space, far below any temperature found naturally on Earth, the records would remain intact for timescales that dwarf the current age of human civilization by factors of millions. Whether anything would ever find them was a question that could not be answered. The designers sent them anyway. The records were a message to the incomprehensible future, placed aboard machines that were being sent farther from home than anything human had ever traveled. But the golden records and their billions of years mission were for later. The immediate mission was something more concrete. The spacecraft had planets to visit, and the planets, as it turned out, had been saving their surprises for exactly this moment. Jupiter was first. Voyager 1 arrived in March of 1979, moving fast, its cameras clicking, its instruments humming on their few hundred watts of nuclear-generated electricity. The encounter lasted only days, but the data it produced filled volumes. The Great Red Spot, observed from Earth for centuries as a persistent oval marking in Jupiter's atmosphere, was revealed under Voyager's cameras as a storm of breathtaking complexity. Layers of cloud rotating at different speeds, internal vortices spinning within the larger circulation, color variations that traced chemical differences in the atmospheric composition at different depths. The storm was larger than the entire Earth, and it had been churning for longer than any human record extended, sustained by mechanisms that atmospheric scientists would spend years working to understand. But the storm was expected. Jupiter's moons were not. A few days before the spacecraft's closest approach to Jupiter, a navigation engineer was processing long-exposure images of the star field near the moon Io. She was using background stars to calculate the spacecraft's precise position, a routine task. In one of the images, extending above Io's curved horizon against the black sky behind it, was a bright, irregular smear. It had internal structure. It was not an artifact of the camera or the processing. It was a plume, a volcanic plume rising from Io's surface, arching hundreds of miles into space in the shape of an umbrella. She had discovered the first active volcanic eruption ever confirmed outside of Earth. Io was supposed to be dead. The outer solar system's moons were expected to be cold, geologically inert, frozen in the conditions of the early solar system like insects preserved in amber. Instead, Io's surface was being continuously remade by volcanic eruptions of extraordinary violence, driven by a heat source that almost no one had considered significant: tidal flexing. Jupiter's immense gravity, acting on Io's slightly elliptical orbit, continuously stretched and compressed the moon's interior as it moved closer to and farther from the giant planet with each orbital cycle. The mechanical energy of this stretching was converted to heat deep in the rock, heating Io's interior to temperatures that exceeded the interior of the Earth, despite Io being a much smaller body far from the warmth of any star. The heat escaped through volcanoes, hundreds of them. They coated Io's surface in fresh sulfur compounds, painting it in yellows and oranges and reds, erasing impact craters as fast as new impacts could create them, making Io one of the youngest surfaced bodies in the solar system despite being billions of years old. The concept of tidal heating, which this single discovery forced the scientific community to take seriously, would eventually become one of the most important ideas in astrobiology. Because if gravity alone could heat a moon's interior to the point of active volcanism, then gravity could also maintain liquid water beneath the ice shells of other moons in the outer solar system. Moons that received no warmth from any star. Moons that floated in the permanent cold of the outer planetary system. Moons that might, beneath their frozen surfaces, harbor oceans. The discovery at Io established the pattern that would define the entire Voyager mission. Wherever the spacecraft looked, what they found exceeded what the models had predicted. The outer solar system was not the quiet, frozen, well-understood region that the textbooks described. It was full of active processes, unexpected chemistry, geological surprises, and physical conditions that the best available theories had missed or underestimated. The scientists on the Voyager team learned quickly to hold their predictions lightly, to read the incoming data with fresh eyes rather than through the lens of what they expected to see. That habit of expectation-free observation would serve them well when the spacecraft reached the wall, because at the wall, almost every prediction would turn out to be wrong. Saturn came next. Voyager 1 arrived in November of 1980, and the rings alone were enough to rewrite the textbooks. From Earth through even the best telescopes, Saturn's rings appear as a small number of broad, smooth bands, elegant, simple, symmetric. Through Voyager's cameras, those broad bands dissolved into a structure of overwhelming complexity. Thousands of individual ringlets, each one a narrow lane of orbiting particles, ice chunks and rocky fragments ranging from grains of dust to boulders the size of houses, separated by gaps that were sometimes sharp and sometimes gradual. Some ringlets were braided, 2 or 3 strands wound around each other in a repeating pattern that simple orbital mechanics said should not persist. Those braids were maintained by tiny shepherd moons, embedded within the ring system, whose gravitational influence herded the particles into their anomalous configuration. Other rings had edges so sharp they looked cut by a precision instrument, maintained by the gravitational sweeping of moons on their outer boundaries. The scale of the structure was staggering. The rings extended from roughly 40,000 miles above Saturn's cloud tops to nearly 90,000 miles out. Yet, in many places, they were only a few dozen feet thick. A physical ratio comparable to a sheet of paper spread across an entire football field. Something about the dynamics of millions of orbiting particles, interacting gravitationally with each other and with the nearby moons, had organized all that material into an extraordinarily thin disk with an extraordinarily intricate internal structure. The rings were a natural laboratory for orbital dynamics, operating at scales and timescales that no Earth-based experiment could replicate. At Saturn, the mission team made a decision that would determine the rest of Voyager 1's trajectory, and ultimately make it the first human-made object to leave the solar system. Titan, Saturn's largest moon, wrapped in a dense, opaque, orange atmospheric haze that blocked the cameras from seeing its surface. The atmosphere was denser than Earth's at the surface, composed primarily of nitrogen with significant methane, and solar ultraviolet radiation was driving chemical reactions that produced a complex mixture of organic molecules that rained down onto the surface as a perpetual orange smog. Some models suggested the surface might harbor lakes or even seas of liquid methane and ethane. Titan was, scientifically, irresistible. But getting a close look at Titan required bending Voyager 1's trajectory sharply using Titan's own gravity. The deflection sent the spacecraft roughly 35 degrees above the ecliptic plane, the flat disk in which all the planets orbit. That meant no more planets, no Uranus, no Neptune, no further flybys of any kind. Just the long outward climb into the dark, angled above the plane of the solar system, heading in the general direction of the heliosphere's northern boundary. The team knew what they were giving up. They chose Titan anyway, and in doing so, they aimed Voyager 1 on the trajectory that would eventually carry it through the wall. Voyager 2 continued the grand tour. Uranus in January of 1986. A planet tipped on its side, its axis tilted nearly 90 degrees from vertical, probably knocked over by a catastrophic impact early in the solar system's history. Its atmosphere was a pale blue-green disk, nearly featureless in visible light, hiding temperature structures and chemical processes that only the infrared and ultraviolet instruments could reveal. Its moons were puzzles. Miranda, the smallest of the major moons, looked like it had been shattered and reassembled, its surface a jumble of ancient cratered plains and young grooved terrain with enormous fault systems and cliffs 5 miles high, all patched together without apparent logic. Neptune in August of 1989, 12 years after launch, operating on systems designed to last 5. The planet was deep blue and extraordinarily dynamic. Wind speeds in its upper atmosphere exceeded 1,000 miles per hour, the fastest winds measured anywhere in the solar system, despite Neptune receiving only a tiny fraction of the solar energy that drives Earth's weather. A dark storm the size of Earth churned in the southern hemisphere. Triton, the largest moon, orbited in the wrong direction, a retrograde orbit that marked it as a captured body, something that had once drifted freely in the outer solar system before Neptune's gravity claimed it. Its surface was extraordinarily cold, yet geysers of nitrogen gas erupted from beneath the surface ice, driven by the faint warmth of sunlight penetrating the transparent nitrogen ice and vaporizing material below. Cold geysers on a captured moon at the edge of the planetary system, the last discovery of the planetary tour. And then Neptune was behind them. The planets were finished. Both spacecraft were heading outward into the dark, toward the boundary that no instrument had ever measured, toward the wall that existed only in theory and in the equations of heliospheric physicists who had spent decades building models of what they believed would be there. The machines that had been designed to last 5 years were entering their second decade. Their cameras had been turned off to save power. The scan platforms that had swiveled to capture the faces of 4 giant planets were locked in place. But the instruments that mattered most for what lay ahead, the charged particle detectors, the magnetometers, the plasma wave systems, and on Voyager 2 the plasma science instrument, were still running, still calibrated, still meeting their performance specifications despite years of radiation exposure and temperature extremes that exceeded anything their designers had qualified them to survive. The wall was ahead. Everything the models predicted was waiting to be tested, and the machines that would test it were, against every reasonable expectation, still alive. Part 2. The Invisible Architecture. To understand what the Voyagers were heading toward, we need to build a picture of something you cannot see, something that fills the entire solar system, extending billions of miles beyond the last planet, yet has no color, no surface, no visible presence of any kind. It is an architecture made entirely of magnetic fields and flowing particles, sustained by the continuous outward breath of the star, and it is the structure that gives the solar system its true boundary. The solar wind, as we have described, flows outward from the star in all directions at roughly 1 million miles per hour. It carries with it the star's magnetic field, pulled outward and wound into a vast spiral by the star's rotation. As the wind expands into the ever larger volume of space surrounding the star, it thins. Its density drops. Near the Earth, at 1 astronomical unit from the star, the solar wind carries roughly 5 to 10 protons per cubic centimeter. That is already extraordinarily thin by terrestrial standards. The best laboratory vacuum on Earth contains trillions of times more particles per cubic centimeter than the solar wind at Earth's orbit. But the solar wind keeps thinning as it moves outward. By the time it reaches Jupiter's orbit, 5 astronomical units out, its density has dropped by a factor of 25. At Saturn's orbit, nearly 10 astronomical units out, the density has dropped by another factor of 4. At Neptune, 30 astronomical units, the density is less than 1,000th of what it was at Earth. By the time the solar wind reaches the distances where the Voyagers would eventually find the wall, somewhere around 100 astronomical units, the density has fallen by a factor of 10,000 compared to its value at Earth. A few 10,000ths of a proton per cubic centimeter. A near-perfect void, populated by scattered individual protons and electrons drifting outward at high speed, each one separated from its nearest neighbor by distances measured in feet, rather than the fractions of millimeters that separate air molecules in the room where you are lying. And yet this extraordinarily thin medium exerts pressure. The protons and electrons are moving fast, and their collective motion outward from the star represents a pressure, a push, that decreases with distance but never quite reaches zero. As long as the solar wind is moving outward, it is pushing outward, inflating the magnetic bubble of the heliosphere against whatever resists it from outside. What resists it is the interstellar medium, the gas and magnetic fields that fill the space between the stars. The interstellar medium in the neighborhood of our solar system is not a vacuum. It is a thin but real plasma, a gas of electrons and ions with a density of roughly 1 particle per 10 cubic centimeters. To put that in perspective, if you could gather all the interstellar gas within a cube 1 meter on a side, the total number of particles would be about 10. A cube of air at sea level on Earth contains roughly 25 billion molecules. The interstellar medium is 25 billion times emptier than the air in your room. But it is there, and it has pressure. The particles are warm, tens of thousands of degrees in the region surrounding the solar system, and their thermal motion creates a pressure that pushes inward against the heliosphere from all directions. The interstellar medium also carries magnetic fields, organized on large scales by the dynamics of the galaxy and on smaller scales by the turbulence of ancient supernova remnants that have swept through the neighborhood over millions of years. Those magnetic fields exert their own pressure and tension, adding to the inward force that the interstellar medium applies to the outer wall of the heliosphere. The heliosphere, then, is a pressure-balanced structure. The solar wind pushes outward. The interstellar medium pushes inward. Where the two pressures are equal, the wall forms. This is the heliopause, a surface of equilibrium. Not a solid wall, but a pressure boundary, as real and as physically meaningful as the surface of a soap bubble, which is also a pressure boundary, the place where the air pressure inside the bubble equals the air pressure outside. Push harder from inside and the bubble expands. Push harder from outside and the bubble contracts. The heliopause is the solar system's soap bubble surface, maintained by the continuous outward pressure of the solar wind against the continuous inward pressure of the galaxy. But the analogy is imperfect in one important way. A soap bubble is roughly spherical because the air pressure outside it is roughly equal in all directions. The interstellar medium surrounding the heliosphere is not uniform. The solar system is moving through the interstellar medium at roughly 52,000 miles per hour, which means the interstellar gas hits the heliosphere harder on the side facing the direction of motion and less hard on the trailing side. This creates an asymmetry. The wall is pushed closer to the star on the leading side, the nose, and is farther from the star on the trailing side, the tail. The traditional picture of the heliosphere, the one that appeared in textbooks for decades before the Voyager measurements challenged it, showed a shape like a comet or a teardrop. A blunt, rounded nose facing into the interstellar wind, and a long streaming tail stretching out behind, where the solar wind flowed outward for enormous distances before finally mixing with the interstellar medium. This picture was logical. It was built from solid physics. It was, in many specific details, wrong, But in the 1980s and 90s, as the Voyagers were making their slow outward journey through the outer solar system, it was the best picture anyone had, and it made specific predictions about what the spacecraft would encounter as they approached and crossed the wall. The first structure the Voyagers would encounter was not the wall itself, but a precursor: the termination shock, a boundary inside the heliosphere, closer to the star than the wall, where the solar wind first feels the resistance of the interstellar medium and abruptly slows down. The termination shock is a consequence of the solar wind being supersonic. Near the star and throughout most of the heliosphere, the solar wind travels faster than the speed at which pressure disturbances can propagate through it. It is, in effect, a supersonic flow. When a supersonic flow encounters an obstacle, it does not slow down gradually. It cannot, because the information that an obstacle is ahead cannot travel upstream faster than the flow itself is moving. Instead, the flow decelerates abruptly at a shock front, a thin region where the velocity drops sharply, the density jumps, and the temperature rises dramatically as the kinetic energy of the directed flow is converted into the random thermal energy of the heated plasma. You have encountered shock fronts in everyday life, though you may not have thought of them in these terms. A sonic boom is a shock front. The sharp crack of a bullet passing overhead is a shock front. The bow wave of a boat moving faster than the water waves it generates is a shock front. In every case, the pattern is the same. A medium moving too fast to get out of its own way piles up abruptly at a thin boundary, where the speed drops, the density rises, and energy is converted from organized motion to disorganized heat. The termination shock of the solar wind was predicted to lie somewhere between 70 and 90 astronomical units from the star. Beyond it, in the region called the Helios Heath, the slowed, compressed, heated solar wind would pile up against the wall, flowing outward more slowly, gradually approaching the conditions that prevailed at the heliopause. The Helios sheath was expected to be roughly 10 to 20 astronomical units thick, a buffer zone between the inner supersonic solar wind and the wall itself. Beyond the wall, the interstellar medium, a different world, a different set of particles, different magnetic fields, different pressures, and the full unshielded flux of galactic cosmic rays, the high-energy particles accelerated by violent processes throughout the galaxy that the heliosphere partially blocks from reaching the inner solar system. The models made many specific predictions about each of these regions. The temperature at the termination shock, the intensity and distribution of certain energetic particles called anomalous cosmic rays, the thickness and turbulence of the Helios sheath, the direction of the magnetic field at the wall, the sharpness or gradualness of the transition into interstellar space. Each prediction was built from careful physics and represented the best understanding of the scientific community at the time. Each prediction would be tested by the Voyagers, and the pattern of the results, finding after finding, measurement after measurement, would be the same. The universe was more complex, more dynamic, more structured, and more surprising than the models had assumed. The invisible architecture of the outer solar system was built on principles the physicists understood, but assembled in a configuration they had not imagined. Before the Voyagers could test any of these predictions, they had to survive. And surviving was not guaranteed. The outer solar system is cold. At the distances the Voyagers were traveling, the temperature of any surface exposed to space drops to a few tens of degrees above absolute zero. The spacecraft's electronics, designed for a much warmer operating environment, had to be kept functional by carefully managing the waste heat from the radioactive power generators. As the plutonium decayed and the power output dropped, the available waste heat dropped with it. The spacecraft grew colder year by year, inching closer to the temperature limits below which electronic components would begin to fail. The communication link grew weaker with every passing year. The signal from the spacecraft, transmitted at roughly 23 watts of radio power, spread out as it traveled, following the inverse square law that governs the intensity of any radiation propagating through space. By the time the signal reached Earth from the outer heliosphere, it had spread across such an enormous area that the power arriving at the receiving antenna was measured in units so small they border on the philosophical. Roughly 1/10 of a billionth of a watt. The Deep Space Network dishes, the largest radio antennas on Earth, had to track the spacecraft's position across the sky with extraordinary precision to collect that signal and separate it from the background noise of the universe. The data rate slowed as the distance grew. Near Jupiter, the Voyagers could transmit data at tens of thousands of bits per second, fast enough to send images in minutes. By the time they reached the outer heliosphere, the data rate had dropped to roughly 160 bits per second. Slower than the earliest dial-up modems, slower than a telegraph. A single image from the old cameras, had they still been operating, would have taken hours to transmit. The science instruments that remained active sent their data home as a trickle, each measurement arriving at Earth hours after it was recorded, crossing billions of miles of empty space at the speed of light. The mission team managed all of this with a patience and a precision that constitutes one of the great sustained achievements in the history of engineering. They nursed the power budgets. They balanced the thermal constraints. They updated the spacecraft software remotely, sending new instructions across the solar system to modify the behavior of computers built in the early 1970s. They made judgment calls about which instruments to sacrifice and which to keep, always prioritizing the measurements that would matter most when the spacecraft finally reached the boundaries they were approaching. And through all of this, the instruments kept working. The magnetometer, extended on its boom, kept measuring the magnetic field. The charged particle detectors kept counting protons and electrons. The plasma wave system kept listening to the oscillations in the surrounding ionized gas. On Voyager 2, the plasma science instrument, the instrument that would provide the most direct measurements of the solar wind at the boundaries, kept functioning despite being decades beyond its design life. The machines would not die, and because they would not die, they reached the wall. What they found there is one of the most important stories in the history of space science, and it begins with a shock. Part 3. The First Wrong Answer. The approach to the termination shock was not a sudden event. It was a slow accumulation of evidence, spread across years, that the spacecraft were entering a region where the solar wind's dominance was beginning to weaken. Through the 1990s and into the early 2000s, as Voyager 1 pressed outward through the outer heliosphere, the charged particle instruments tracked gradual changes in the particle populations surrounding the spacecraft. The density of solar wind particles continued its long, slow decline. The intensity of anomalous cosmic rays, a class of energetic particles that had been detected by earlier spacecraft closer to the star, showed a gradual increase. The magnetic field, still dominated by the solar wind's outward-carried structure, showed increasing fluctuations, as though the medium surrounding the spacecraft was becoming less stable, more responsive to disturbances propagating outward from the star or inward from the approaching boundary. The anomalous cosmic rays deserve particular attention because they were at the center of one of the most important wrong predictions in the history of heliospheric physics. Anomalous cosmic rays were first detected in the 1970s by instruments on earlier spacecraft closer to the star. They had energies much higher than the typical solar wind particle, but lower than the galactic cosmic rays that constantly bombard the solar system from outside. They had an unusual chemical composition, enriched in elements like oxygen and helium and nitrogen that are common in the interstellar medium but relatively scarce in the solar wind. Something was taking interstellar material, accelerating it to high energies, and injecting it into the heliosphere. The theoretical explanation that gained the widest acceptance was elegant and multi-stepped. Neutral atoms from the interstellar medium, hydrogen and helium and oxygen atoms carrying no electric charge, could drift freely into the heliosphere because the heliosphere's magnetic field cannot deflect neutral particles. Once inside, these atoms could be ionized, stripped of an electron by the star's ultraviolet radiation, or by charge exchange with solar wind protons. The newly ionized particle, now carrying a charge, would be grabbed by the solar wind's magnetic field and swept outward. These were called pickup ions, interstellar atoms that had been ionized and picked up by the solar wind. As the pickup ions were carried outward toward the termination shock, the shock itself was expected to act as a particle accelerator. The physics of shock acceleration, a well-studied process in plasma physics, predicted that particles bouncing back and forth across the shock front would gain energy with each crossing, gradually being accelerated to the high energies observed in the anomalous cosmic ray population. The termination shock in this picture was the source, the factory where anomalous cosmic rays were manufactured from interstellar raw material. This prediction was clean. It was well supported by the underlying physics. It made a specific, testable claim. The intensity of anomalous cosmic rays should be highest right at the termination shock or just inside it, at the location of their source. As the Voyagers moved outward toward the shock, the intensity should rise, peak at the crossing, and then decline on the far side as the particles diffused away from their origin. In 2002 and 2003, the charged particle instruments on Voyager 1 began showing behavior that suggested the spacecraft was nearing the termination shock. The intensity of energetic particles fluctuated in ways that could be interpreted as the shock moving toward and away from the spacecraft, breathing in and out as the solar wind's pressure varied with the star's 11-year activity cycle. The termination shock was not a fixed boundary. When the star was active and the solar wind blew harder, the shock was pushed outward. When the star quieted and the solar wind weakened, the shock contracted inward. The spacecraft might have briefly crossed the shock during one of these oscillations, entering the heliosheath momentarily before being pushed back out as the shock moved outward again. The data from this period was ambiguous and generated vigorous debate among the science team. Some argued that a partial crossing had occurred. Others maintained that the spacecraft was still inside the termination shock. The debate highlighted something important. The termination shock was a dynamic, living boundary, not a fixed line on a map, but a breathing surface that moved in response to the star's varying output. Approaching it was not going to be a clean, simple event. By late 2004, Voyager 1 was at approximately 94 astronomical units from the star, more than 8.5 billion miles from home. The instruments were showing sustained changes in particle populations and magnetic field behavior. And in December of 2004, multiple instruments simultaneously registered the signatures that the science team had defined years in advance as definitive evidence of a termination shock crossing. The magnetic field showed the expected compression. The charged particle instruments recorded the dramatic deceleration of solar wind particles, from roughly 300 miles per second to below 100 miles per second over a zone only a few astronomical units thick. The solar wind had hit the wall of interstellar pressure and abruptly slowed, exactly as shock physics predicted. But the details were wrong. The details were fascinatingly, productively, illuminatingly wrong. The first discrepancy was the magnetic field direction. The models had predicted that the solar wind's magnetic field would be compressed and reorganized at the shock in a specific way, with the field direction rotating to match the changed flow conditions on the far side. The actual field direction beyond the shock was rotated by nearly 30 degrees from the predicted orientation. 30 degrees does not sound like much, but this was a systematic, reproducible measurement from a well-calibrated instrument on a spacecraft that had been returning accurate data for 27 years. It was not noise. It was not an artifact. It was a real discrepancy between what the models said should be there and what was actually there. The magnetic geometry of the outer heliosphere was structured differently from what the models described. That 30-degree discrepancy was a direct measurement of asymmetry. The heliosphere was not the symmetric bubble the models had assumed. The interstellar environment surrounding it had structure, directional pressure, organized magnetic fields, and those external forces were pressing on the heliosphere in specific, non-uniform ways that distorted its magnetic architecture from the simple, symmetric configuration the models had used. The magnetic field discrepancy at the termination shock was the first of many measurements that would reveal the heliosphere as a far more complex and asymmetric structure than anyone had modeled. But the magnetic field was only the beginning. 3 years later, in August of 2007, Voyager 2 reached the termination shock. It crossed at approximately 84 astronomical units from the star, nearly 10 astronomical units closer than Voyager 1's crossing point. 10 astronomical units is roughly 930 million miles. If the heliosphere were a symmetric bubble, both spacecraft should have crossed the shock at roughly the same distance regardless of the direction they were traveling. The 10-unit difference was immediate proof that the heliosphere was not symmetric. Its southern boundary, toward which Voyager 2 was headed, was compressed closer to the star than its northern boundary. Something was squeezing one side of the heliosphere harder than the other. The explanation was external. The interstellar medium surrounding the solar system is not uniform. The combination of the interstellar wind, the flow of interstellar material relative to the solar system as the solar system moves through the galaxy, and the interstellar magnetic field, which exerts pressure that varies depending on its orientation relative to the heliosphere's surface, creates a pressure environment that is stronger in some directions than others. The southern hemisphere of the heliosphere appears to face higher interstellar pressure than the northern hemisphere. That pressure difference compresses the southern boundary inward, which is why Voyager 2 found the shock nearly 1 billion miles closer to the star than Voyager 1 did. Voyager 2's crossing provided something else, something that Voyager 1's crossing had been unable to offer, and something that made it one of the most scientifically valuable events in the entire mission: direct plasma measurements. Voyager 1's plasma science instrument had failed in 1980, more than 20 years before its termination shock crossing. Without it, the science team had to infer the plasma conditions at the shock from indirect evidence, changes in the magnetic field and charged particle populations. Voyager 2's plasma instrument was still functioning. For the first time, a spacecraft with a working plasma instrument was crossing the solar system's outer boundary. The data it returned created a significant problem for the theorists. The termination shock is a place where fast-moving plasma abruptly decelerates. In plasma physics, this deceleration converts kinetic energy, the energy of directed motion, into thermal energy, the energy of random particle motions that we measure as temperature. The models, using well-established shock physics, predicted that the plasma behind the termination shock should be heated to roughly 1.5 million degrees. The solar wind had been moving at 300 miles per second. It was now moving at less than 100. All that kinetic energy had to go somewhere. Voyager 2 measured a temperature of approximately 180,000 degrees. That is roughly 12% of the predicted value. 88% of the expected thermal energy was not in the plasma that the instruments could measure. It had gone somewhere else. Or the physics of energy conversion at this particular type of shock was different from what the established theories described. Where did the missing energy go? The question became one of the most actively discussed problems in outer heliosphere physics. Several possibilities were proposed. Some energy might have gone into heating heavier ions, atoms of oxygen and helium, and other elements present in the solar wind at low concentrations, which the plasma science instrument was not optimized to characterize. Some energy went into accelerating the anomalous cosmic rays, which are known to draw energy from the termination shock region. Some may have been converted into wave turbulence in the magnetic field, a form of energy that dissipates differently from direct plasma heating. But adding up all the reasonable estimates of these alternative energy sinks, researchers could not fully account for the missing 88%. The numbers did not balance. Either the measurements had systematic errors that could not be identified, or there was a physical process operating at the termination shock that was not in any of the models. The missing energy remains one of the unresolved puzzles of outer heliosphere physics. It is a vivid example of the kind of specific quantitative wrongness that the Voyager data produced in what had been considered well-understood theoretical territory. And then there were the anomalous cosmic rays, the particles that were supposed to peak in intensity at the termination shock, at the location of their predicted source. They did not peak at the shock. Both spacecraft found that anomalous cosmic ray intensity continued increasing well beyond the termination shock, deeper into the heliosheath. The particles were more intense far from the shock than at the shock itself. This was a direct contradiction of the acceleration model. If the termination shock were the primary source, intensity should peak there and decline with distance. The fact that it kept rising deeper into the heliosheath meant either that the particles were being accelerated somewhere else entirely, or that the transport of these particles through the heliosheath's complex magnetic field was so different from the model's assumptions that particles originating at a distant source appeared concentrated closer to the heliopause. The most widely discussed alternative explanation pointed to the flanks of the termination shock rather than the nose region the Voyagers had sampled. The termination shock is a three-dimensional surface surrounding the entire solar system, and its properties vary around its perimeter. The nose, where the solar wind most directly impacts the interstellar pressure, has different geometry and flow conditions then the flanks on the sides, and the tail behind the solar system. Some theoretical work suggested that the flanks might be more efficient particle accelerators than the nose, because the geometry of the magnetic field at the flanks is more favorable for the repeated reflections that generate high-energy particles. If most anomalous cosmic ray acceleration happens at the flanks, the particles would diffuse inward and be found throughout the heliosheath, rather than concentrated at the nose where the Voyagers crossed. This explanation was plausible. It was consistent with the data. It could not be confirmed because no spacecraft has visited the flanks, and none is planned that would do so in the foreseeable future. The true source of the anomalous cosmic rays remains uncertain. 3 predictions, 3 wrong answers: the magnetic field orientation, the plasma temperature, the anomalous cosmic ray source, each one a specific quantitative discrepancy between the best available models and the actual measurements, each one pointing toward a heliosphere that was more complex, more asymmetric, more dynamically active, and more deeply influenced by the interstellar environment than anyone had modeled. The termination shock crossing was only the beginning. Beyond it lay the heliosheath, and beyond the heliosheath lay the wall itself. The heliopause, the true edge. The spacecraft were heading toward it, and the wall, when they finally reached it, would deliver its own set of surprises. Let yourself settle into the quiet of this journey. There is no hurry. The spacecraft took years to cross the heliosheath. We can take our time as well. Part 4. The Crossing. Beyond the termination shock, the Voyagers entered the heliosheath, the buffer zone, the region where the slowed, compressed, heated solar wind piles up against the outer wall, flowing outward more and more slowly as it approaches the heliopause. The models had depicted the heliosheath as a moderately turbulent transition zone, a region where the solar wind, having been decelerated at the termination shock, would gradually lose its remaining outward velocity, compress further, and smoothly approach the conditions prevailing at the heliopause. The transition was expected to be spread over 10 to 20 astronomical units, a gradual fade from heliospheric conditions to something approaching the interstellar environment. The heliosheath that the Voyagers actually measured was far more complex, far more spatially variable, and far more energetically active than the models had described. The magnetic field showed large amplitude fluctuations on timescales of hours to days. Not the gentle variations the models predicted, but sharp, dramatic swings in field strength and direction that suggested the medium was being constantly disturbed by processes the models had not included. Energetic particles were distributed in sharp, discrete layers rather than the broad, diffuse distributions the models assumed. The plasma temperature showed unexpected variations, some regions cooler than expected, others warmer, with no clear pattern tied to distance from the termination shock. The heliosheath was not a simple, gradual transition zone. It was a complex, structured environment with its own internal dynamics. A turbulent, magnetically active buffer zone where the dying solar wind wrestled with the approaching interstellar pressure in ways that the one-dimensional models had been fundamentally unable to capture. As Voyager 1 pressed deeper into the heliosheath, nearing a distance of 113 astronomical units from the star, the instruments detected something that stopped the science team cold. The outward flow of solar wind particles dropped to essentially zero. The solar wind was no longer streaming outward from the star in the direction Voyager 1 was traveling. At a position still well inside the heliosphere, the solar wind had simply stopped. It was no longer moving toward the wall. It was being deflected sideways, redirected around the edges of the heliosphere rather than flowing straight outward to the heliopause. Something in the outer heliosheath was turning the solar wind aside before it could reach the boundary. This was not predicted. Every model of the heliosheath assumed the solar wind would continue flowing outward, slowly and compressed, all the way to the heliopause. The discovery that the flow halted well before the boundary implied that the interstellar medium's pressure, pushing inward from just outside the heliopause, was strong enough in this direction to prevent the solar wind from penetrating all the way through. The solar wind was being turned aside, deflected along the heliosheath rather than pushing through it to the wall. The region where this happened came to be called the stagnation region, a place where the expected outward flow simply stopped. And within the stagnation region, the magnetic field data revealed something remarkable and unexpected. Field lines threading through the stagnation region appeared to be connecting the inside of the heliosphere to the outside, running through the heliopause rather than being deflected by it. Energetic particles were streaming along these connected field lines in both directions simultaneously. Galactic cosmic rays flowing inward from interstellar space, solar energetic particles leaking outward toward it. The heliosphere's outer wall was not sealed. It was threaded by magnetic pathways that allowed particles to pass in both directions. Some members of the science team described these pathways as a magnetic highway, a network of connected field lines along which material could travel between the interior of the heliosphere and interstellar space without crossing the heliopause in the traditional sense. The concept challenged the picture of the heliopause as an impermeable barrier. The wall was not a sealed wall. It was, in places, more like a membrane, permeable to particles that could find the right magnetic pathways to thread through it. The most natural explanation was magnetic reconnection, the process by which magnetic field lines from two different regions break and reconnect with each other, creating pathways that span the boundary between the two environments. Reconnection is a well-known process in plasma physics. It happens regularly at Earth's own magnetosphere, where the solar wind's magnetic field connects with Earth's field, allowing particles to cross the magnetopause and enter the radiation belts. Finding evidence for reconnection at the heliopause added the solar system's outer boundary to the list of environments where this fundamental plasma process operates, and it changed the picture of what the crossing would look like. And then, in August of 2012, the crossing happened. It was not gradual. It was not a slow, dreamy transition from one environment to another over months or years. It happened in roughly 3 days. Over a period of about 72 hours in mid-August 2012, the charged particle instruments on Voyager 1 recorded a sharp, sustained drop in the flux of particles associated with the solar wind. Simultaneously, the cosmic ray instrument registered a jump in the intensity of galactic cosmic rays. The high-energy particles from sources throughout the galaxy, accelerated by supernova remnants and other energetic processes far beyond the solar system. The galactic cosmic ray flux climbed to the highest level Voyager 1 had ever recorded and then leveled off, suggesting the spacecraft had crossed into a region fully immersed in the unshielded galactic radiation environment. The change was dramatic and rapid. Inside the heliosphere, the instruments saw solar wind particles. 3 days later, they saw interstellar particles. The transition was as sharp as a doorway, but the magnetic field told a more complicated story. The models had predicted a large rotation in the magnetic field direction at the heliopause, perhaps as much as 90 degrees, as the field transitioned from the heliospheric structure dominated by the solar wind to the interstellar structure dominated by the galactic magnetic field. The actual rotation that accompanied the particle changes in August 2012 was substantial but much less than 90 degrees. The field direction changed, but not by as much as it should have if the spacecraft had truly crossed from one magnetic domain into an entirely different one. This ambiguity sparked a debate that lasted over a year. Some scientists argued that Voyager 1 was in a new, unmapped region, neither fully inside the heliosphere nor fully in interstellar space. Perhaps a transition zone where the two magnetic environments had already mixed, blurring the distinction between inside and outside. Others argued that the particle changes were definitive, that Voyager 1 had crossed the heliopause regardless of what the magnetic field was doing, because the particle population had entirely changed character. The decisive measurement came from the plasma wave instrument, and it came 9 months later. In April of 2013, a pressure wave generated by a solar eruption reached Voyager 1's position after propagating outward from the star for more than a year. As the pressure wave compressed the local plasma, it drove electron oscillations that the plasma wave instrument detected. The frequency of those oscillations provided the electron density directly. The measured density was approximately 0.08 electrons per cubic centimeter. That density was roughly 40 times higher than anything measured inside the heliosphere at those distances, and it precisely matched the theoretical predictions for the local interstellar medium. Voyager 1 was outside. It had left the heliosphere. It had crossed the wall. The spacecraft had entered interstellar space in August of 2012. The confirmation came in April of 2013. NASA announced the milestone officially in September of 2013. The announcement was historic. Voyager 1 had become the first human-made object to leave the solar system and enter interstellar space. The signal carrying that news from Voyager 1 to Earth had traveled for approximately 17 hours. The spacecraft was at that point roughly 122 astronomical units from the star, about 11.5 billion miles from home. But the crossing was immediately followed by findings that complicated the picture. The plasma density measurement was not what the models had predicted. The density in the local interstellar medium just outside the heliopause was higher than most pre-Voyager models had estimated. Higher density means higher pressure. Higher pressure means the interstellar medium is pushing harder against the heliosphere's outer wall than the models assumed. That has direct consequences for the heliosphere's size. A stronger external pressure requires a stronger solar wind to maintain equilibrium at the heliopause, meaning the equilibrium point is closer to the star than it would be in a lower density environment. The heliosphere is smaller than the models predicted, in part because the interstellar medium is denser than they assumed. The magnetic field finding at the heliopause also required explanation. The modest field rotation, rather than the large rotation the models predicted, meant that the interstellar magnetic field in the solar system's immediate neighborhood was oriented similarly to the heliospheric field rather than perpendicular to it. The two fields were nearly parallel near the heliopause. This had implications for the heliosphere's shape, for the nature of the interaction at the nose, and for whether a bow shock exists ahead of the heliosphere in the interstellar medium. A nearly parallel external field changes the character of that interaction from what the perpendicular field models had described. 6 years later, in November of 2018, Voyager 2 crossed the heliopause. It crossed at approximately 119 astronomical units, about 3 astronomical units closer than Voyager 1's crossing. The difference confirmed the asymmetry already demonstrated by the different termination shock crossing distances. The heliosphere's boundary is not equidistant from the star in all directions. The direction Voyager 2 traveled, below the ecliptic plane toward the southern galactic hemisphere, apparently faces slightly higher interstellar pressure, compressing the heliopause closer to the star. Voyager 2's crossing carried the extraordinary advantage of a functioning plasma science instrument. For the first time, a spacecraft could directly measure the plasma properties on both sides of the heliopause. The data arriving from Voyager 2 over the days of its crossing showed the transition with a precision and directness that Voyager 1's indirect methods could not provide. And the data showed something unexpected. On the inside of the heliopause, in the outermost heliosheath, the plasma was hotter than expected. Hotter than it had been at the termination shock, farther inward. This was physically backward from the simple model in which the plasma should cool as it decelerates through the heliosheath. Something was heating the plasma in the outer heliosheath, close to the wall, and the energy source was not immediately identifiable. Charge exchange between solar wind protons and interstellar, neutral hydrogen atoms was one candidate. This process transfers energy from the neutral hydrogen into the plasma. Wave heating, in which the constant fluctuations of the turbulent heliosheath magnetic field gradually convert magnetic energy into plasma heat, was another. But no single mechanism cleanly explained the measured temperatures. The energy budget of the outer heliosheath, like the energy budget at the termination shock, did not balance. At the heliopause itself, both spacecraft found the same thing. The transition was sharp, strikingly sharp. The change from heliospheric plasma to interstellar plasma happened within a very narrow zone, just a few astronomical units thick, perhaps less. The heliosphere did not fade gradually into the interstellar medium, the way a warm current of water might gradually blend into the cooler water surrounding it in a lake. It ended abruptly, the way a soap bubble ends at its surface. On one side, the heliosphere with its solar wind plasma and solar-dominated magnetic field. On the other side, the interstellar medium with its denser plasma, stronger magnetic field, and galactic cosmic ray environment. Two fundamentally different physical environments separated by a boundary thin enough to cross in a few months of spacecraft travel. The sharpness surprised many researchers. Some had expected a thick, diffuse transition zone where the two environments gradually blended over large distances. Instead, the heliopause was a stable, well-defined surface in magnetic and plasma pressure equilibrium. A clean edge, a real wall, and beyond the wall, the interstellar medium. Both spacecraft, now outside the heliosphere, began directly sampling the environment that fills the space between the stars. The magnetic field strength just outside the heliopause was slightly higher than most models had assumed. The electron density matched predictions for the warm, partially ionized interstellar medium, a phase of the interstellar gas known from observations of distant stars, but never before measured directly by an instrument sitting inside it. The temperature of the plasma just outside was in the range of 30,000 to 50,000 degrees. Warm. Not the cold, quiet, neutral medium of the older models, but a warm, ionized environment with its own dynamics and structure. The galactic cosmic ray flux, the full, unshielded flux from sources throughout the galaxy, reached the highest intensity Voyager 1 had ever measured, roughly 4 times higher than at Earth's orbit, where the heliosphere's magnetic field partially blocks the lower energy cosmic rays from penetrating to the inner solar system. The spectral shape of the cosmic ray flux matched theoretical predictions for cosmic rays originating from supernova remnants and diffusing through the galaxy's magnetic field. The basic model of galactic cosmic ray origin was broadly correct. But at the lowest energies accessible to Voyager's instruments, the spectrum showed features that carried information about the heliopause's properties, spectral fingerprints left by the boundary on the particles that crossed it. The solar system sits inside a wall. The wall is real. 2 machines have crossed it. What they found there, in every specific detail, was different from what the models predicted. Different in ways that are not minor refinements or small corrections, but fundamental revisions to the understanding of how the heliosphere works, how it interacts with the interstellar medium, and what the local interstellar environment actually looks like. Let us rest here for a moment. Outside the wall, in the interstellar dark, the signal from the spacecraft takes nearly a full day to reach us. The machines are running on less power than a small light bulb. The data arrives at a rate slower than a telegraph, and yet each number that arrives carries information that no other source can provide. Information about where we live, about the shape of our home, about the forces that press against it from outside. Breathe slowly. Let the scale settle into your body. 11 billion miles. 17 hours at the speed of light. The wall is real. The machines have crossed it, and they are still sending back the numbers. Part 5. The Shape of Home. The 2 heliopause crossings, Voyager 1 in 2012 and Voyager 2 in 2018, provided something that no theoretical model could replace. 2 actual measured points on the boundary of the heliosphere. 2 places where instruments had directly sampled the transition from inside to outside, recording the plasma density, the magnetic field strength and direction, the particle populations on both sides of the wall. 2 points separated by tens of astronomical units and located in different directions from the star. 2 points are not enough to define a surface. The heliopause is a 3-dimensional boundary surrounding the entire solar system, and the vast majority of it, the flanks, the tail, the polar regions, the parts facing away from both spacecraft, remains unmeasured. But 2 points are infinitely more than 0. They provide constraints. They rule out models. They anchor the theoretical pictures to reality in a way that nothing else can. The first thing the 2 crossing distances revealed was the asymmetry we have already discussed. Voyager 1 crossed the termination shock at 94 astronomical units. Voyager 2 crossed at 84, a 10-unit difference. Voyager 1 crossed the heliopause at 122 astronomical units. Voyager 2 crossed at 119, a 3-unit difference. The termination shock showed more asymmetry than the heliopause. This suggests that the heliosheath dynamics partially smooth out the asymmetry between the 2 boundaries. The interstellar wind pushes the termination shock inward, more on one side than the other. But the heliosheath, the thick buffer between the shock and the wall, redistributes some of that pressure difference before it reaches the heliopause. The pattern of the asymmetry points outward. The solar system is moving through the galaxy at roughly 52,000 miles per hour. The interstellar wind, the flow of interstellar gas relative to the solar system, presses harder against the nose of the heliosphere, the side facing the direction of motion. But the interstellar magnetic field adds a directional pressure that does not align perfectly with the interstellar wind. The combination creates a pressure environment that varies with direction in a complex way. The southern hemisphere of the heliosphere, the direction Voyager 2 explored, faces higher total interstellar pressure than the northern hemisphere. The numbers from the two crossings put specific quantitative constraints on how much higher. But asymmetry is only part of the story. The broader question is the heliosphere's overall shape. And on that question, the Voyager data combined with observations from a very different kind of mission to challenge one of the most familiar images in space science. The traditional picture of the heliosphere, the one you may have seen in textbooks or documentaries or visualizations, shows a shape like a comet. A blunt, rounded nose facing into the interstellar wind. A long, streaming tail stretching out behind the solar system in the direction it is moving away from, where the solar wind flows outward for enormous distances, before eventually blending with the interstellar medium. This comet-shaped heliosphere was an intuitive picture, modeled on the behavior of comets moving through the solar wind and on the behavior of magnetospheres moving through the solar wind. It was aesthetically satisfying and physically plausible. The data began to challenge it from multiple directions. The challenge came in its most dramatic form, not from the Voyagers directly, but from a small satellite orbiting much closer to home. In October of 2008, NASA launched a spacecraft called the Interstellar Boundary Explorer, known by its acronym, into an orbit that kept it in the inner solar system, well within the heliosphere, not far from the Earth. Its purpose was not to travel to the boundary, but to observe it from a distance. To build a map of the entire boundary region at once, the way you might stand on a hilltop and survey the entire coastline of a bay, rather than walking along the beach and seeing only the stretch of sand immediately at your feet. The Interstellar Boundary Explorer accomplished this by detecting a special type of particle called an energetic neutral atom, and the technique it used revealed a feature of the heliosphere that no one had predicted or imagined. Energetic neutral atoms are created in the outer heliosphere through a process called charge exchange. When a fast-moving solar wind proton encounters a slow-moving neutral hydrogen atom that has drifted inward from the interstellar medium, the proton can capture the atom's electron, neutralizing itself. The newly neutral particle, now carrying no charge, is no longer affected by any magnetic field. It continues traveling in a perfectly straight line, in whatever direction it was moving at, the moment it became neutral. If that direction happens to point toward the inner solar system, the particle will travel in a straight line across billions of miles of space, carrying with it information about the conditions at the location where it was created. Its energy tells you the temperature and speed of the solar wind at that location. Its direction tells you where on the boundary it came from. The Interstellar Boundary Explorer collected millions of these particles from every direction in the sky and assembled them into an all-sky map of the heliospheric boundary. The first complete map was published in October of 2009, and it was immediately strikingly strange. The map showed broad, diffuse emission from the direction of the heliosphere's nose, where the solar wind collides most directly with the interstellar pressure. It showed fainter emission from other directions. All of this was broadly expected. But running across the entire sky, in an arc roughly 15 to 20 degrees wide, was a band of intensely bright emission that had not appeared in any prediction, any model, any theoretical paper. The band was bright enough, organized enough, and geometrically precise enough that the science team initially doubted their own instruments. They checked the calibrations. They looked for artifacts. They found none. The band was real, and nothing like it had been predicted. It came to be called the ribbon, and its geometry was the key to understanding it. When scientists mapped the ribbon's position against the known direction of the local interstellar magnetic field, they found that the ribbon lay along the great circle in the sky where the interstellar magnetic field is perpendicular to the line of sight from Earth. This was not a coincidence. It was the geometric signature of a specific physical process in which solar wind protons that escape through the heliopause are ionized in the interstellar medium, gyrate around the interstellar magnetic field lines, and then undergo a second charge exchange that sends some of them back toward the inner solar system as neutral atoms. The focusing effect of the magnetic geometry concentrates these returning particles along the ribbon's position. The ribbon's existence had a profound implication. For the focusing mechanism to produce a narrow, bright ribbon, the interstellar magnetic field had to be strong and well organized. Weak or turbulent fields would scatter the particles rather than focusing them into the tight geometric arc that the instruments observed. The ribbon was direct evidence that the interstellar magnetic field near the solar system was stronger and more coherent than most pre-mission models had assumed. The heliosphere was being shaped by a significant external magnetic force, and that force affects the heliosphere's shape. A strong, organized interstellar magnetic field does not simply push inward uniformly. It pushes harder in directions perpendicular to the field lines and allows the heliosphere to extend more easily along the field lines. This creates a shape that is not the simple comet of the traditional picture. Some models, incorporating the strong interstellar field revealed by the ribbon and confirmed by the Voyager crossings, suggested that the heliosphere might be rounder than the comet model, perhaps even roughly spherical in overall character, with the tail being much shorter or differently organized than the classic picture depicted. Other models found that the tail might be organized into two lobes rather than a single streaming structure, with the solar wind flowing along the heliospheric current sheet into two opposite-pointing lobes rather than fanning out symmetrically behind the solar system. The debate between the comet model, the rounder model, and the two-lobe model has not been settled. No spacecraft has measured the tail region, and the energetic neutral atom maps show emission from that direction. But interpreting it unambiguously requires assumptions about the underlying physics that are themselves uncertain. The Interstellar Mapping and Acceleration Probe, launched in May of 2024, carries significantly more capable energetic neutral atom detectors than the earlier mission. Its higher resolution maps should help distinguish between the competing models, particularly regarding the tail structure, which remains one of the most contested aspects of the current picture. What we can say with confidence is this: the heliosphere is not the simple, symmetric, comet-shaped bubble that appeared in textbooks for decades. It is asymmetric. It is shaped by a strong, organized interstellar magnetic field that does not press uniformly from all directions. Its boundaries are at different distances from the star in different directions, and the differences are large enough to be measured by the two Voyager crossings. Its internal structure, the heliosheath, is turbulent and complex, with energy budgets that do not balance and particle populations that are not where the models placed them. Its outer wall, the heliopause, is sharp and thin and magnetically permeable, threaded by field lines that allow particles to cross in both directions. The heliosphere is our magnetic home, the structure that separates everything we have ever known from the interstellar medium. And its shape, its size, its character are not permanent features of the cosmic landscape. They are the result of a dynamic equilibrium between the outward breath of the star and the inward pressure of the galaxy. And that equilibrium changes. The solar system is moving. It is moving through the galaxy at a speed that carries it through different regions of the interstellar medium over timescales of tens of thousands to millions of years. The solar system is currently embedded in a pocket of warm, partially ionized gas called the local interstellar cloud, a wisp of material roughly 30 light-years across that the solar system has been traversing for perhaps 300,000 years. The local interstellar cloud is itself embedded in a much larger structure called the local bubble, a region of extremely hot, tenuous plasma that was excavated by supernova explosions roughly 5 to 10 million years ago. When the solar system eventually exits the local interstellar cloud, which some calculations suggest may happen within the next 20,000 to 50,000 years, it will find itself in the hotter, more tenuous gas of the local bubble. The interstellar pressure will change. The heliosphere will respond. Some models suggest it could expand to 2 or even 3 times its current size. Other models find the transition less dramatic. What is clear is that the heliosphere has been different in the past, will be different in the future, and is not a fixed feature of the solar system's architecture. There is something quietly awe-inspiring about this realization. The shell that separates us from interstellar space is not a permanent structure. It breathes. It flexes. It responds to the changing conditions of the galaxy through which we are traveling. The solar system is not a sealed capsule moving through a uniform void. It is an open system, in constant communication with its galactic environment, separated from the interstellar medium by a boundary that is real but not rigid, defined but not permanent, protective but not sealed. The heliosphere is our outermost radiation shield. Galactic cosmic rays, the high-energy particles accelerated by supernova remnants and other violent processes throughout the galaxy, are partially blocked by the heliosphere's magnetic field. The heliosphere does not stop them completely. At the highest energies, cosmic rays pass through the heliosphere largely unhindered. But at lower energies, in the range of a few 100 million to a few billion electron volts, the heliosphere significantly reduces the cosmic ray flux reaching the inner solar system. Outside the heliopause, Voyager 1 measured the full, unshielded cosmic ray flux. It was roughly 4 times higher than at Earth's orbit. The spectral shape, the way intensity varies with particle energy, matched theoretical predictions for cosmic rays originating from supernova remnants and diffusing through the galaxy's magnetic field. The basic model of galactic cosmic ray origin and propagation was broadly confirmed by the measurement. But the shielding efficiency of the heliosphere is not constant. It varies with the solar activity cycle, strengthening when the solar wind is stronger and weakening when the solar wind is weaker. And it varies with the heliosphere's size, which itself depends on the interstellar pressure. A smaller heliosphere, compressed by denser interstellar material, provides less shielding. A larger heliosphere provides more. Over geological timescales, the cosmic ray flux reaching Earth has varied as the solar system has moved through different regions of the galaxy. Periods when the solar system passed through the spiral arms of the galaxy, where interstellar density is highest, likely compressed the heliosphere and allowed more cosmic rays to reach the inner solar system. several researchers have proposed connections between these passages and major events in Earth's biological and climate history. The cosmic ray flux affects the production of carbon-14 and other cosmogenic isotopes in Earth's atmosphere, isotopes that geologists and archaeologists use to date ancient events. The Voyager measurements of the unshielded cosmic ray environment now provide the baseline against which historical variations can be assessed. The shape of home. Not the shape of the planet, not the shape of the orbit, but the shape of the magnetic bubble that carries us through the galaxy. A bubble that has been different in the past and will be different in the future. A bubble whose true character was revealed not by theory, but by two small machines that kept sending back the numbers long after anyone expected them to stop. Part 6. Between the Stars. Both spacecraft are now in interstellar space. Both are still transmitting. The data they send back arrives as a trickle, 160 bits per second, slower than a telegraph, crossing more than 15 billion miles at the speed of light, requiring nearly a full day for each signal to make the journey from the spacecraft to the deep space network antennas on Earth. The data describes a place that no human instrument had ever sampled before. The interstellar medium, the environment that fills the space between the stars, the ocean in which the heliosphere floats. It is not what the older models described. It is not cold. It is not quiet. It is not a uniform, featureless void interrupted only by the occasional wandering star. The interstellar medium in the solar system's immediate neighborhood is warm, 30,000 to 50,000 degrees, partially ionized, a mixture of neutral atoms and charged particles, threaded by magnetic fields that are stronger and more organized than the pre-Voyager models assumed, structured on scales comparable to the heliosphere itself, varying from one side of the heliosphere to the other in magnetic field strength and direction. This is the warm, partially ionized phase of the interstellar medium, a phase known from observations of distant stars, whose light passes through the interstellar gas and picks up absorption features that reveal the gas's properties along the line of sight. But distant observations average over enormous path lengths, blending the properties of many different regions of gas into a single measurement. The Voyagers are providing point measurements, direct readings of the interstellar plasma at a specific location, a few astronomical units outside the heliopause in the very local interstellar medium immediately adjacent to the boundary. What they measure there is not necessarily representative of the interstellar medium at large. The heliopause has been pushing against the local interstellar medium for billions of years. The region immediately outside the heliopause has been compressed and modified by that interaction. The gas there may be slightly warmer, slightly denser, slightly more magnetically compressed than the undisturbed interstellar medium would be at a greater distance from the heliosphere. To fully characterize the undisturbed interstellar medium in the solar system's neighborhood, measurements farther from the heliopause would be needed, farther than either Voyager can reach with remaining power. But even the very local interstellar medium, the region immediately beyond the wall, tells us something important about the galactic neighborhood the solar system inhabits. The solar system is currently in the local interstellar cloud, a warm, partially ionized pocket of gas roughly 30 light-years across, one of several similar clouds drifting through the much larger local bubble. The local bubble itself was created by multiple supernova explosions roughly 5 to 10 million years ago, and it extends several hundred light-years in most directions, filled with extremely hot but extremely tenuous plasma. the solar system entered the local bubble from a denser region of the interstellar medium at some point in the relatively recent past, geologically speaking. It has been traversing the local interstellar cloud within the bubble for perhaps 300,000 years. And it may exit the local interstellar cloud within the next 20,000 to 50,000 years, though the uncertainties in the cloud's boundaries and the solar system's relative velocity make this estimate rough. When we exit the local interstellar cloud, the conditions surrounding the heliosphere will change. The pressure, the density, the magnetic field, the temperature of the interstellar medium will shift, and the heliosphere will respond. It may expand dramatically as the external pressure drops. It may contract if the new environment happens to be denser or more magnetically intense than the current one. The wall will move. The boundary that defines where our star's influence ends and the galaxy's begins will shift to a new equilibrium. This has happened before, many times. Over the solar system's 4.5 billion-year history, it has orbited the center of the galaxy roughly 20 times. Each orbit takes about 230 million years. Along those orbits, the solar system has passed through the spiral arms of the galaxy, where interstellar density is highest, and where massive stars are born and die in supernova explosions that enrich the interstellar medium with heavy elements and drive shock waves through the surrounding gas. Between the spiral arms, the interstellar medium is thinner and calmer. Each passage through a spiral arm likely compressed the heliosphere, reducing its shielding capacity and allowing more galactic cosmic rays to reach the inner solar system. The geological and biological record of Earth carries traces of these passages, though the connections are debated. Variations in cosmic ray flux affect the production of cosmogenic isotopes in the atmosphere and may influence cloud formation and climate through mechanisms that remain under investigation. Several large-scale extinction events in the fossil record have been tentatively correlated with the solar system's passage through spiral arms, though the statistical significance of these correlations is contested and the physical mechanisms are not well established. What is not contested is that the heliosphere has a history. It has been larger and smaller. The wall has been closer and farther. The cosmic ray environment in which life on Earth evolved has not been constant. It has varied with the solar system's journey through the galaxy, modulated by the changing interstellar environment and by the changing strength of the solar wind over the star's own evolution. The heliosphere we measured with the Voyagers is a snapshot, a single frame from a film that has been running for billions of years and will continue running for billions more. Both Voyagers continue to operate in this interstellar environment, sending back their measurements. Each year that they continue extends humanity's first direct sampling of the interstellar medium to a slightly greater distance from the heliopause. Each year builds a longer baseline along their respective trajectories, providing information about how the interstellar medium varies with distance from the wall. Whether the immediately adjacent region is significantly modified by the heliosphere's presence, and over what length scale that modification fades. That information is available from no other source. The Voyagers are the only instruments in position to provide it, and they are slowly running out of time. The power continues to decline. Each year, a few more watts are lost to the steady decay of the plutonium-238. Instruments have been shut down one by one over the decades, each sacrifice carefully weighed against the remaining science return. The cameras were the first to go, powered off long before the outer heliosphere was reached. the ultraviolet spectrometer, the infrared radiometer, the photopolarimeter. One by one, the instruments that had revealed the faces of 4 giant planets were switched off to conserve power for the instruments that would matter at the boundary and beyond. What remains is the essential minimum: the magnetometer, the charged particle instruments, the plasma wave system. On Voyager 2, the plasma science instrument. These are the instruments that provide the measurements that no other spacecraft can make. The measurements of interstellar magnetic fields, interstellar plasma density, the flux and spectrum of galactic cosmic rays outside the heliosphere's shield. Scientists estimate that at least some instruments on each spacecraft may continue returning data into the early 2030s before the power budget finally becomes insufficient to operate any science instrument. When that day comes, the instruments will go quiet. The transmitters will fall silent. The Deep Space Network dishes will stop hearing the faint, patient signal that has been arriving continuously for more than 50 years. But the spacecraft will not stop. They cannot stop. There is nothing in interstellar space to slow them down. No friction, no resistance, no atmospheric drag. They will continue moving at their current speeds, roughly 38,000 miles per hour for Voyager 1 and roughly 35,000 miles per hour for Voyager 2, following the trajectories that were set by the gravitational encounters with Jupiter and Saturn and Titan nearly 50 years ago. The trajectories are fixed. They were calculated by the navigators in the 1970s. The gravity assists that accelerated the spacecraft also set their directions, and those directions will not change in any meaningful way for millions of years. Interstellar space is extraordinarily empty. The probability of a collision with any substantial object over the next several million years is vanishingly small. In roughly 40,000 years, Voyager 1 will pass within about 1.5 light-years of a small star in the constellation Camelopardalis. It will not come close enough to be captured or significantly deflected. It will continue past, carrying its trajectory forward into the dark. In about 300,000 years, Voyager 1 will approach the inner edge of the Oort cloud, the vast spherical halo of comets that surrounds the solar system at distances of thousands of astronomical units. It will pass through the sparse outer Oort cloud without encountering anything. Voyager 2, traveling in a different direction, will pass close to another star in roughly 40,000 years as well. Again, not close enough for capture or deflection. The two spacecraft launched 16 days apart from the same launch facility in Florida, will drift through the galaxy on separate paths for the rest of time. In late 2023, Voyager 1 demonstrated once more the extraordinary resilience that has defined the mission. The spacecraft began transmitting unintelligible data, a garbled stream of numbers rather than the properly formatted telemetry the Deep Space Network expected. Engineers spent weeks analyzing the problem from more than 15 billion miles away. They determined that a single chip in the Flight Data System computer had developed an error, possibly caused by a cosmic ray strike after 47 years of operation in the radiation environment of deep space. The corrupted memory held the code that formatted the outgoing telemetry, which explained why the data became unreadable. The fix required identifying the affected code, distributing it across other available memory locations in the aging computer, and sending new instructions that told the computer to execute the code from its new distributed addresses. The commands traveled for 22 hours to reach the spacecraft. The confirmation that the fix had worked traveled 22 hours back. When Voyager 1 resumed transmitting properly formatted science data in April of 2024, it was the result of some of the most remarkable remote engineering ever performed. Debugging and repairing a computer built with 1970s technology, operating in interstellar space, at temperatures far beyond its qualification limits, using only a radio signal as the interface, from a distance so great that the round-trip communication time exceeded a full day. The engineers who built the redundant systems and backup memory locations in the early 1970s could not have imagined that their careful design decisions would be invoked 50 years later to repair a cosmic ray hit in interstellar space. But the philosophy that led them to build those backups, the assumption that things will break and that the design must accommodate breaking, is the reason the mission is still alive. It is also a lesson about the value of conservative engineering, of building systems that are robust against failures you cannot predict, of designing for a future you cannot see. The interstellar probe concept, developed in detail by scientists at Johns Hopkins Applied Physics Laboratory, envisions a dedicated spacecraft launched specifically to cross the heliopause and sample the interstellar medium with modern instruments. Such a mission would carry particle detectors, plasma instruments, magnetic field sensors, and energetic neutral atom cameras far more capable than anything on the Voyagers. It would be aimed at crossing the heliopause in a direction chosen for maximum scientific return, possibly through the heliotail or in a direction that complements the Voyager crossing directions. Getting there quickly enough to return useful data before the instrument's lifetimes expire would require propulsion techniques not yet demonstrated, including a possible close pass near the star to use solar gravity for extreme acceleration. The concept has received serious attention in NASA's long-range planning documents, and the scientific case for it has been built directly on the anomalies the Voyager data revealed. But such a mission lies in the future. For now, the Voyagers remain the only instruments that have ever directly measured the termination shock, the heliosheath, the heliopause, and the very local interstellar medium. For at least the next decade, and possibly longer, they will remain the only sources of in situ data from those regions, and on each spacecraft, bolted to the bus structure, the golden record waits. The record is quiet now. It will be quiet for a very long time. It carries no transmitter. It emits no signal. It is a passive object, a message in a bottle thrown into an ocean so vast that the metaphor breaks down completely. The ocean between the stars is not measured in miles or even in millions of miles. It is measured in light years. The nearest star to the solar system is more than 4 light years away. At Voyager 1's current speed, it would take roughly 70,000 years to cover that distance. And Voyager 1 is not heading toward the nearest star. It is heading in a different direction entirely, toward stars that are farther away, on a path that will carry it through the galaxy for timescales that dwarf the entire history of human civilization. Gold does not corrode. At the temperatures of interstellar space, well below any temperature found on Earth, the record will remain intact. The spacecraft structure around it will slowly degrade, eroded atom by the impact of interstellar dust grains and high-energy cosmic ray particles. But the process is extraordinarily slow. The record should remain largely readable for billions of years. Whether it will ever be found is a question that involves quantities we cannot estimate. The density of technological civilizations in the galaxy. The probability that a trajectory passing through the vast emptiness between stars would happen to pass near enough to such a civilization for the record to be detected. The longevity of such civilizations. The nature of the detection methods they might employ. These are variables for which we have no data and may never have data. The designers of the Golden Record knew this. They understood that the probability of the record ever being found and decoded was extremely small. They sent it anyway. The record was not primarily a practical communication device. It was a statement, an expression of the human impulse to reach outward, to leave evidence, to say something to the unknown future about what existed here, what was valued, what was heard and seen and felt by the beings who built these machines and sent them into the dark. 115 images, 55 greetings in human languages, the sounds of earth, thunder, wind, birdsong, a mother's first words to a newborn child, music from every continent, Bach, Beethoven, a Navajo night chant, a Peruvian panpipe, Indonesian gamelan, the sound of a human heartbeat, the sound of a kiss. These things are now in interstellar space. They will remain there for longer than the star that produced them will burn. The star will eventually exhaust its hydrogen fuel, swell into a red giant, shed its outer layers, and collapse into a white dwarf, a process that will unfold over the next 5 to 7 billion years. The golden records will still be drifting through the galaxy when the star is dead. They will carry the evidence that once around that star on a small rocky planet, in a thin shell of atmosphere warmed by the star's light, something arose that could hear music and feel awe and build machines and aim them at the dark and say, "Here. We were here. This is what we sounded like. This is what we saw. This is what moved us." The machines continue. Voyager 1 is currently approximately 165 astronomical units from the star, about 15.5 billion miles from home. It is moving outward at roughly 38,000 miles per hour. Each day it adds another 900,000 miles to the distance between itself and everything it came from. Voyager 2, traveling in a different direction, is approximately 138 astronomical units away. Both are in interstellar space. Both are still transmitting. Both are still sending back the numbers. The numbers describe a place that is not empty, not cold, not quiet. The interstellar medium in the solar system's neighborhood is warm and structured and magnetically organized and in active dynamic communication with the heliosphere through the permeable wall that separates them. The galaxy presses against the wall with forces strong enough to shape it. The heliosphere pushes back with the breath of the star, and the balance between these forces, a balance that has shifted many times over the solar system's history and will shift many times again, defines the boundary of our home. We live inside a magnetic bubble, a pressure-balanced structure inflated by the continuous outward breath of the star and contained by the inward pressure of the galaxy. The bubble is not symmetric. It is not simple. It is not permanent. It is shaped by forces that we have only recently begun to measure directly, thanks to 2 machines that were designed to last 5 years and have lasted nearly 50. Every major prediction about the wall was wrong. The magnetic field orientation was wrong. The temperature was wrong. The energy budget did not balance. The cosmic ray source was not where the models placed it. The shape was not the shape the textbooks drew. The thickness was not the thickness the models predicted. The interstellar medium beyond it was not the cold, quiet void the older pictures described. And every wrong prediction was a gift. Because every wrong prediction pointed to missing physics, missing understanding, missing pieces of the picture of where we live and how we are connected to the galaxy that surrounds us. The corrections the Voyagers forced on 50 years of heliospheric theory were not minor adjustments to an already accurate picture. They were fundamental revisions that revealed a more complex, more dynamic, more interconnected reality than anyone had assumed. The universe is more interesting than our models of it. That has always been true. The Voyagers proved it at the edge of the solar system, and the proof came in the form of numbers. Numbers transmitted at 160 bits per second across 15 billion miles of space. Numbers that arrived at Earth as a signal so faint that it bordered on the immeasurable. Numbers that told us, quietly and precisely, that where we live is stranger and more wonderful than we knew. Both spacecraft are heading outward. They will not come back. There is no mechanism to turn them around and no reason to try. They are carrying the evidence of our existence into the galaxy, following trajectories set by the gravitational encounters of the 1970s and 1980s, trajectories that will not change for millions of years. They will drift through the space between the stars, silent and golden, for longer than the star behind them will shine. And for a little while longer, they are still talking to us, still sending back the numbers, still telling us about the place beyond the wall, the place where the solar system ends and the galaxy begins. Let that thought carry you gently. The boundary is real. The machines have crossed it. The data has arrived. And what the data says is that we are part of something much larger than the small circle of light around our star. We are embedded in a galaxy. We are surrounded by interstellar forces that shape our magnetic home. We are shielded, imperfectly, by a bubble of the star's breath. And beyond that bubble, the rest of the universe stretches outward in every direction, vast and warm and magnetically alive, waiting for whatever we send next into the dark. Breathe slowly. Feel the weight of the day dissolve into the vastness of space. You are lying in the same gravitational field that holds the planets in their orbits, and the heliosphere in its shape. The same physics that builds the wall at the edge of the solar system keeps you gently pressed against the surface of the Earth. You are part of the system. You are inside the bubble, and the bubble is real. Where are you listening from tonight? Wherever you are, the wall is out there, 15 billion miles away. And two small machines, older than most of the people alive today, are still sending back the numbers from the other side. Wishing you a peaceful night beneath the stars.